Okay, so in today's lecture, we're going to talk about one of the very important part in the neural network is how to train neural network. So this lecture will be quite mathematically intense. I will try to slow down a little bit and trying to make this notation as clear as possible. All right, so let me just make this notation a little bit clear here. So for example, I'm going to have a multiple layers, like multiple hidden layers. In the neural network, for example, we have a layer of L minus one, we have a layer of L. And for example, right here, we have a bunch of neurons. And we have a bunch of additional neurons here. And we know everything is fully connected, right? So for example, this is fully connected. But for and specific for this neuron J, it has the contribution coming from the neuron K from the previous layer. So this is I'm actually the weight I want to learn. Right, this weight is actually the WJK. I'm going to notice it like WJK of L. And I have additional bias term, which is BJK and BJL, right? So and related to that. Okay. So basically, this is the contribution coming from the neuron K in the layer L minus one to the neuron J in the layer of L. So in short, we are only use so my activation function is use the sigmoid throughout the whole throughout the whole layer, even for the output layer. And the loss is I'm going to use log loss. All right, so and what does that mean is after we have this linear layer, we have an input of something called Z J of L that I'm going to apply a sigmoid function, then it will output the A J of L. So this process, activation function process, is going through element-wise. Okay, so before we actually let's get into the details, I need to specify those notations clearly. So let's just make sure we have the right notation to work with. Notation. So for layer equal to layer L equal to 1 to the L. So the first thing that we have is, as I said, is the WJK of the L. So this is the K K to the J's weight at layer L. All right, so this is basically says we have a neuron K in the previous layer. I have a neuron J in the current layer, so this will be the weight from K to the J at layer of L. Then we can everything to make it vectorize, and the vectorized version, I'm going to call it the W right here. I'm going to call it the WL. So what does that mean is I'm going to have this WJK of L to be as a matrix. So basically this is all this JK matrix, and J and K will be the index of my matrix of L. So this is the matrix of all weights between and between L minus 1 to and L. So this is the first thing. This is the weight. Then we have the bias, right? So this is bias is B, J, L. So we have a neural J biases at layer of L. Same thing, right? And then we can make it to be vectorize it again. If we vectorize it, so this is basically a B, which is a vector. Bj L. So basically, I vectorize with index of J. So this gives you a vector bias. In layer L. Number 3. Then we have something called A. A is the output of J. So I'm going to call AJ of L. It's the output of neuron J at layer of L. Okay, so and the same thing we can everything like to be vectorized. So this becomes a vector of A. And this is I basically vectorize it. AJ and like vectorize according to the index of J. So this is vector of output. In layer L. Number 4, so we have a Z. So that's the weight and weighted input to the like neural of J. Of J at layer of L. So I think it should be called at here. Okay, so this is Z is input or something called pre-activation value. And this is, I want to box it out. So A, I'm going to call it output, and the Z here is input before we apply these activations. All right, so and similarly, we can like vectorize it. So if we actually vectorize it, this is Z, and here I think I should put a bracket here of ZJ of L of J. So this is basically a vector of the weighted input. What layer of L? All right. So then we have the connection between the input and output. So basically so and this is my output here, this is my input here. So basically my output here is equal to, we apply some activation function of the input. And of course, we can vectorize it if we wanted. Vectorize it. So basically vectorize this equal to G of ZL. So this is vector and basically vectorized version of everything. So, but this is just applied component-wise, like element-wise. Right, so everything, so everything, passing through for the activation function, it's all element-wise. So this is activation function. So the parameter that we are interested in, theta is equal to, it's basically all these parameter weight at different layers. Right, so that's the parameter that we want to train, to be tuned. And the data that we are interested in, as I said, is we have same set of the data set for the and for the classifications. So this is the feature, and this is my label. All right. This is not a vector. It's just a label here. So the first thing that we need to do is I want to talk about something called forward propagations. So the first thing to do is to work on something called forward propagation. So this is the first part. The first thing is, for example, so I'm going to call this input layer is L equal to 0. So input layer is the case is that L equal to 0. So that's the 0th layer that I just want to set that. And I don't have input and output because an input layer just I have the value coming from the feature. So that means my A0 is just simply from this features X. And also the output layer. This is this as last layer, which is else layer. So I want this my output after my output layer is actually a function like f. Input is being x, and I have parameter of theta. Right. So this is the input is my feature. The output is some functions. See here we're applying this sigmoid here. They are not necessarily normalized to be a probability, but that's something that and we will output. It's just like a vector functions. All right. So then for all intermediate, So this ZL, first thing I'm going to do is I'm going to take the linear layer, that is W of L, A L minus 1 plus BL. All right, so these are all vector here. This is nothing but like matrix vector multiplications. Then at the end, we're getting AL is equal to, I'm going to apply this activation function. So I mean, this is step 1, this is step 2, G of ZL. So so at each layer, so what we do, as I said, just apply the first and the linear layer, then we apply, and here just being as activation functions component wise. So we can write everything in a very shorthand, like in compressed version, that we have A L minus 1 as a vector here. Here that I'm going to use and plug in the information of WL and BL, which is the parameter, right? So this actually what we got is the ZL, right? So then and then we apply this this and a sigmoid function right here, right? So then the output becomes AL, right? So and this is a good illustration. And then it passes through and to the next layers until the last one will be and it will be a capital L. Right, so this is a very interesting. So and you can think about it as a two part. I mean, first part is the linear transformation or linear yes, and the linear layer. Then we have, the activation part. All right. Okay, so that's the forward propagation. So basically, if you are given a theta, so forward propagation says you are given the x and the theta already. So basically, all the parameter we already know. Just plug in and find out all these and output at output layers. All right, so once we get this output of the f, which is a function here, we need to calculate the loss. So the second part that we're interested in is the loss function. Okay, so we pick the loss, and for example, we can pick the square loss if we need it, and of course we can pick the log loss if possible as well. For example, just if we just pick the square loss, I think we talked about this and the log loss things in the last lectures. So for now, let's just stick with the square loss. So basically, after the the forward propagation, you should be able to calculate this f now. Then my loss function right here is basically, if we take the square loss, that's a summation from 1 to the n, L of f x of I and theta and the y of I. Okay, so I mean this is my output. So we just plug in the output. Which is A L value of x or y. Subtract yi. So here we already make this yi to be one hot encoding. So this is actually a vector now. So I'm trying to work with the norm here. So this will be okay, square root 2 norm, square loss. Okay, so this is one hot encoding, one hot vector of yi. Okay. So the key is we want to varying this weight, which is the weight of all these linear layers, and we want to minimize between the network output right here and output layer to the one of the vectors above, like associated to the training class of xi and it belongs to. So basically, this is the one hot vector of the true label of yi, and this is my and the network output. I want these two things to be as close as possible. Okay, so if they are close, my loss function will be small as well. All right, so this is the whole point. So how can we solve these things, right? So I mean, the key here is we try to solve partial L theta D partial W L and partial L theta D partial BL. Right, so these are the derivative informations that we want to solve here, which is not trivial at all. In fact, this is and it has been puzzled for many years, and then this is and big things turns out. All right, so so let's try to do it and try to figure out one by one. So to solve these gradient from scratch, it actually requires some algorithm called backward propagation. Okay, so let me just write it out explicitly, and also and make everything and simplify it first. So let's just look at the last layer one first, because we know, so this whole thing has to go back from the last layer. So so this is we have here. So we have a layer of L minus one. So say this is a neural K. We have a layer of L. Right, so then we know the output right here. So say this is neural of J. Then this output will be A1L. This will be A2L, and so on. Right, and we know this weight from here to here, it's WJK of L, and we have a bias which is BJL. Okay, at the end, these components just combine together. This becomes so error of one sample, and one sample error C of I here. So this is, I mean, this is not a neuron, just and lost here. So, I mean, we think about everything in terms of stochastic gradient descent. So that means I only pass in one of xi. If we only have for one and one data, that is x of I and the yi. I have this sample error. That means that's called C of I is equal to, basically, I only consider the error for one point. So if we choose the square error, that's 1/2 of A L of x of I, subtract yi of one hot encoding, square to norm. Okay, so if and then all these derivatives of each individual derivatives, well, becomes the following. So basically, if and we know we want to solve for the total gradient and the derivatives, then I mean, this case is partial L theta d partial WL, right? We can just use the one, I mean, derivative of each individual derivative with respect to WL and BL. So the C of I partial WL. And also, similarly, on the BL. Right, so then all we need to do is to solve these derivatives. Right, so for each individual and the derivatives here. Okay, let's start from the output layer. Output layer. So by chain rule, we can just write it out all these terms one by one. So we know this is partial CI, partial, we're interested in partial W, J, K, L, right? So JKL is, K is from the previous layer, and the J is from an upper layer. So this is partial CI, partial AJ, L. Then we just like take the chain rule, partial AJL, partial ZJL, then partial ZJL, then partial WJKL. Right, so then the first term right here, since we know the CI, I mean precisely right here, and take partial C and like AJL. This is and this is nothing but like AJL subtracted to the YJL. Right, so this YJL is the jth component of the one hot encoding times this part right here is activation because AJ is equal to G of ZJ, right? So this is an activation function. So this is G prime of ZJ of L. Then at last, this Z and the ZJ of WJK. So, and we go back to our formula right here. So basically, this is, and think about this is about the linear layer. It's Jth component take partial derivative with respect to JK component. Right? So this and ends with the kth component. I mean derivative will be the kth component of A. So this is AK component of L minus 1. So you do the same thing for the bias. Bj of L. So you take the chain rule one more time. So the first two terms is exactly the same. The difference is the last term. Right, so the last term, because this is the bias term right here, if we look at this forward propagation term right here, so where I'm actually take partial derivative with respect to each component of Bj right here. So I mean, if we take the partial derivative with this Bj right here, this is nothing but 1. So this is give me AJL subtract to YJL times G prime of CJL times 1. Okay. So the reason, I mean, so this is something, and I would suggest you to go back to check out because I mean it's all coming from the, I mean this fact that AJ L is equal to G of CJL. The second is we have this linear layers, but it's we are and this is expression for component wise. Plus BJ, yeah, right. So this is why we get this result. So that means basically the rate of change, which has 3 factors. These 3 factors is this factor, and this factor. 3 factors, multiply them together. So this is basically is how much the current output of the, desired output. So this is my current output. This is my desired output. So how much differences with these two? The second one is how fast this neuron reacts to the change of the input. So that means it's derivative at the pre-activation value. So like how much and how fast it can react. This is the contribution from the neuron K from the previous layers. Okay. So one thing is I want to emphasize is if we look these things carefully, so that means we have multiplication of 3 things. If one of that is close to 0, then the gradient will be small. This is a very and a serious problem. If the gradient is very small, then then it will be very slow to learn, right? So this is very common sense in the, somehow. So, so particularly if we choose G equal to sigmoid, so which is sigmoid functions, and even this part is really large, and but that pre-activation vector could not, and it could be very far away from zero if it's is too large or too small. Then the G prime of ZL will be very small. So as a result, this gradient will be very small. Or if AK L plus 1 is close to 0, then the gradient will, then the partial CI partial W JK will be very small. So you have a problem, it's called gradient vanishing. All right, so these has two name, and for these two situations. One, for this one, it's called the neuron is saturated. So that means, both cases, this pre-activation value is either too low or too high. And as the result, the derivative it's very close to 0. Or and you might learn very slowly. If the input neurons is in low activations, input is in low activations. So because we have 3 terms, either one of that is small, then the whole gradient will be small. So this is a big problem here. So if either of the cases that we have, that derivative will be small. So we have one big issue called gradient vanishing. So this is something called gradient vanishing. There are multiple ways to solve it, but we are not focusing on that. But you should have a good idea. So what is the reason coming from the gradient vanishing? All right, so that's so the solution will be okay. So let me just be a little bit careful. And there are multiple solutions for the gradient vanishing. So one is and to solve this saturated problem, you could use different activation function. For example, RaLu doesn't have that problem, right? So and you can use in RaLu here. And what you can do, and the other way is you can use change this and a skip connection and use the idea of the ResNet, and you can skip connections, and that means and we only need to multiply and smaller number of the terms, then the gradient vanishing problem and it could be significantly lowered. There are other method. For example, we can do it's at random skipping the connections. So we can randomly mute this and the weight of W's, and that's also will be helpful as well. But this is for the gradient vanishing part, there's no concrete or definitive answers for that. It's all case by case. All right, so let's go back to the gradient part right here. So here we write all my gradient in terms of coordinate. But the beauty of the mathematics is everything can be vectorized. So what we can do is we can vectorize the gradient. Okay, so the way we do is we just directly write it out here. Partial CI, partial WL, that is equal to. So basically we are going to using this A of L, which is my output, subtract to the 1-hot encoding. Right, so this is something that we already know. This is the basic to measure how off between the output to the ground truth. Element-wise product of G prime of ZL. Then matrix product of AL minus 1 but transpose. Okay, so I want to, and it's better to look at all these like dimension here. So this is K by 1. This is also a K by 1. So K by 1, element-wise, multiply K by 1, it gives you K by 1. So this actually is a vector, but so after you take the transpose, this becomes a row. So this is R of 1 by and the dimension is HL minus 1. So here I just assume H and HL minus 1 is number of neurons in layer L minus 1. All right, so by the end, we are getting RK times HL minus 1. Right. So this is actually the gradient. We do the similar things for the biases. But for the bias, we just don't have the last term. We only have the first two terms. So this is just ZL. Right, so this becomes a vector of R by 1, K by 1. Right. That's good. But and you can see this is quite messy to compute. And what I'm going to do is I'm going to define some additional quantity to help us to calculate. So and let's define something new quantities to simplify the calculation things. I'm going to define a quantity that it's called delta of L. This is defined as partial CI, partial A L of G prime of ZL. So this is equal to AL minus YI, then G prime of ZL. So like if we have this, so this defined quantity, in fact, we can make things a lot easier. Partial CI, partial WL is equal to just this delta of L dot of A L minus 1 transpose. So this is what makes the whole argument a lot simpler and a lot simplified. And later, and you can see, and there's a good and a good reason why we want to do this. All right. So we spent quite a bit of time to actually just and trying to work on the last layer. And we are going to move a little bit forward to the layer of L-1 and further inside. So on layer L-1. So so we have already and talk about the output layer. So this is so layer L-2, layer L-1, layer L. So we have a bunch of neurons here. I have a bunch of output layers. So we have a talk about this is being the J, this is being the K, right? So we have a talk about this connections here from K to the J, right? So, and then let's call this is a Q here. So I have like one additional one from Q to the K. So this is becomes W, K, Q, L-1. And right here is a BK, L-1. Right, so this is basically, I'm interested in trying to take partial derivative with respect to WKQ L-1 and the BK L-1. So this is the weight from the neuron Q at layer L-2 to the K at L-1. Right? So this is the question that I want to address here. Okay, so we do this chain rule again, which is quite tedious, but this is absolutely necessary. All right, so this is partial CI, partial WKQ, L-1. So this, what we got is we take advantage of chain rule one more time. So it's, I'm going to actually sum for all possible of J here, because J here is, I mean, so all, and all the term actually matters to the CK here, right? CI here, right? So in order to take partial derivative with respect to WKQ, that means we need to take part and take all the contributions from AJL. So this is partial CI, partial AJL, and partial AJL of partial WKQ L-1. So to sum of all possible J here. All right, so next, it will be, so we, and further work out on the chain rule things, because it only matters is this neuron right here of the K, and every other neurons on the layer of L-1 doesn't contribute. So this is summation of J, partial CI, partial AJL, partial AJL, partial AK L-1, partial AK -1, L-1, partial WKQ L-1. So the first term right here is AJL minus YJI. And yeah, so this is just, from the loss functions, right? So this term right here, so we use the same trick that we already did. So this is nothing but we have to take the y prime of ZK as EJL and WJK L. Okay, so this is basically the same term that we have used right here, but the difference is here we're going to change this to partial AKL minus 1. Okay, so do the same thing for the next one. This is G prime Z K L minus 1 times the AQ L minus 2. All right, so that's good. So basically this term right here is actually the link between the layer of L and L minus 1. All right, so similarly, we can work out everything in a vector form. So this is, in terms of in vector form, is partial CI, partial W, L minus 1, W, L transpose, delta L. So this is, and we already use this formulation coming from, and use this like delta already. Then delta L evaluate ZL minus 1 so this is element-wise product. Wait, ZL, right? No, that's wrong. So this is a dot product here, and right here is the element-wise product of G prime of Z L minus 1 then these two components, then times A L minus 2 transpose. Okay. If we look this whole dimension right here, so this is actually it's a matrix times a vector, so this is actually give you H of L minus 1 by 1 as the column right here. This is also give you HL minus 1 by 1. You multiply them together element-wise. Take transpose of this matrix. This can get you 1 by HL minus 2. Right, so by the end, you're getting a matrix between of L minus 1 times H of L minus 2. Okay, similarly, So what you can do is you can further define this kind of like quantity that. So we can define this delta L minus 1 is equal to everything in this bracket. So WL transpose times delta L and the component-wise product of G prime of Z L minus 1. All right, so this is the like definition right here. And partial CI, partial W L minus 1 right here. It is delta L minus 1. And by taking advantage of this definition, this is delta L minus 1 times matrix multiplication of times this transpose of these vectors. Okay, so that is everything for the and take derivative with respect to W. You can do the similar things for the weight. If for the weight is basically partial CI, partial B L minus 1. It's nothing but just delta L minus 1. Right, so this is actually the vectorized version. Similarly, you have, the comparison that you had is like this. Right? Oh, and I missed the bias one. So this is partial CI, partial BL is equal to delta L. Okay. So in general, you can see this whole trend is going on here. So, and you can move further and further and inside of this network, you just need to compute more and more link between the layers. For arbitrary layers, for any layer L, so you can see this similar trend is going on here. So you define this delta like little L here. And this is equal to W L plus 1 transpose times delta L plus 1. Then element-wise product G prime of ZL. So you can calculate this like delta L, like iteratively from the delta capital L backward from like L to L minus 1 to L minus 2 until like 0. Then this partial CI, partial W L is nothing but delta L multiply the A L minus 1 vector transpose. And a partial CI, partial BL is nothing but just delta L. So this is how we calculate the gradient. All right, so to summarize everything that we have and combine all we have done, and you can see the whole thing is quite complicated. It's not that straightforward in general. So to summarize, so the product of all these terms are computed iteratively from right to left. So it's like from L to L minus 1 to L minus 2 and then going on. Then at the end, we want to have and we get this sub-efficient algorithm to compute those derivatives. Right, so this becomes partial CI, partial W, L, and this L is like general L, and a partial CI, partial B, L here at layer L. Right. So what you do is you have a 3-step. The first step was step 1. You do forward propagation. That means to calculate all the AL. So that means A0 is the X of I, which is the input data. And all the AL is being calculated from left to right. So this is G of W L of A L minus 1 plus BL. For L from 1 to the L. So this is like left to right. So from 0 you get 1, from 1 you get 2. This is, and the left to right. So then step 2, backward propagate. So you calculate the delta. So you start with the delta. Capital L is equal to partial CI, partial AL. So this is generic. And entry-wise product of G prime of ZL. Then delta little l is equal to, you calculate backward from L to L minus 1 to L minus 2 until 1. So it's actually left, it's right to left. So W L plus 1 transpose times delta L plus 1 animal-wise product of G prime ZL. So this L has to be from like starting from L minus 1 to 1, right? From, and everything is from right to left. So with all these things that we calculate, we should compute partial CI, partial WL, compute all the derivatives, which is partial CI, partial W, L is the delta L times A L minus 1 transpose. So this is actually a column dot a row. This gives you a matrix, right? Same thing, you do it for the biases. This is nothing but delta L. That will be it. This is 3-step on backward propagations. So, and use all like full propagation and backward propagations to calculate the gradient here. So this is basically we're trying to calculate the delta. This is also vector here, right? Vector of L. AL is calculated, and the output of neuron is calculated from left to right, and delta, which is our help function, is calculated from right to left. Okay, at the end we calculate the gradient in this manner. All right, so that is backward propagation. So you can see the math here is quite intense. It's quite significant. So that's why I want to spend a little bit of time to talk about this. In the next lecture, we're going to implement everything from scratch. All right, so that's it.